Today I'm going to present my work about symbolic execution and pointer analysis. This is a joint work with Timotej Kapus, Noam Rinetzky, and Cristian Cadar. Symbolic execution is a program analysis technique that has many applications, such as test input generation, bug finding, and many more. It's an active research area, and it's also used in the industry. Static analysis, and in particular pointer analysis, was combined with symbolic execution in the past to improve the effectiveness of symbolic execution applications. This was done in symbiotic, catch, and also more recent work such as chopped symbolic execution and segmented memory model. In these works, we first run the pointer analysis and then use its results during the symbolic execution. However, you don't take advantage of the dynamic information that comes from symbolic execution to improve the pointer analysis. Our goal is to close this cycle and to come up with a pointer analysis technique for symbolic execution, which not only improves the effectiveness of symbolic execution applications, but which can also improve the precision of the utilized pointer analysis, and this way making the combination of these two complementary analyses more successful. To illustrate the problem, let's look at this example. Suppose that during symbolic execution, we need the points information of function foo. In standard static point analysis, objects are abstracted using static allocation sites that correspond to lines in the program. Here you can see that all the objects that are allocated in the loop will have exactly the same static allocation site B. As a result, the analysis can distinguish between the different objects of the array, and in particular, it can distinguish between the first object and the second one. So the analysis will tell us that in function foo, the field P may point to an object whose allocation site is C because of the update of P that is done on the first object. This is clearly a false positive, as we can see that foo operates on the second object while the update of P is done on the first object. Our goal is to run pointer analysis on demand instead of doing it ahead of time. We want to run the analysis on a specific symbolic state and to locally analyze a specific function. Our approach is past-sensitive pointer analysis. In this approach, we distinguish between the past and the future, between objects that were already allocated till the current execution point and objects that might be allocated during the pointer analysis. We run the analysis locally on a given function instead of analyzing the whole program. To do so, we need to extend our abstract domain with what we call the unique allocation sites. Every object that is allocated during the execution is associated with a unique allocation site, which is a distinct copy of a static allocation site. For example, when we execute this loop, the first object will be associated with a unique allocation site B1, the second object will be associated with B2, and so on, where B1 and B2 are different copies of the static allocation site B. When during the execution we reach a function that we want to analyze, we compute a path-specific abstraction using the current symbolic state and use the computed abstract state to run the pointer analysis on this specific function. To compute the abstraction, we need to traverse the symbolic memory starting from the function parameters and the global variables, and then translate to a points to graph in the abstract domain. Now let's see how it works with our previous example. Assume that we reach the invocation of function foo and want to statically analyze it. So first we need to compute the abstraction of the current symbolic state. Here we don't have any global variables, so we start the memory traversal from the function parameter O. So O points to the second object, which is a struct, and the field P of this struct points to null. In the abstract state, the second object corresponds to the unique allocation site B2, so we'll have a pointer relation between the top-level pointer O and the first field of B2, and another pointer relation between the second field of B2 and null. Now that we have the initial abstract state, we can analyze function foo. Here it will tell us that P may point only to null, so in this case we don't have any false positives. Depending on the client application, the number of analyzed functions can be high, and running point analysis from scratch every time is expensive. We observed that the initial abstract states of a given function are often isomorphic, so in such cases, we can reuse previous analysis results and avoid rerunning the point analysis. Let's see how it works with a simple example. Suppose that we want to compute the method of function foo. In the first invocation of foo, assume that this is our initial abstract state. So the analysis will tell us that function foo may write to the field D, and this will be our mod set. Now we get to the second invocation of foo, and assume that this is our initial abstract state. You can see that these two states are actually equal after renaming, so they are isomorphic. Now we can get the mod set of function foo in the second invocation without rewriting the point analysis. It will be obtained from the first one by simply renaming A to B. We implemented our approach using the symbolic executor CLI, and we extended SVF, which provides point analysis. We evaluated our approach with several client applications, chopped symbolic execution, symbolic pointer resolution, and write integrity testing. The first application is chopped symbolic execution. This is a technique which allows to skip user-specified functions, and to remain sound, it relies on static motif analysis to resolve the side effects of the skipped functions. Let's see in this example if we can skip the invocation of foo with static point analysis. As we saw before, static point analysis can distinguish between the different objects of the array. So in this case, this will be the method of foo. So after we skip the invocation of foo, we execute this assignment, and here the abstraction of the read location depends on the computed mod set. So we have here a false dependency, as we know that foo operates on the second object, while the assignment operates on the first one. Now let's see how it works with our path-sensitive approach. Again, we read the invocation of foo, and now the method of foo will contain B2, which is the unique allocation site of the second object. When we reach this assignment, the abstraction of the read location will be B1, which is the unique allocation site of the first object. So in this case, we have no false dependencies, and we can continue the execution without recovering the skipped execution of function foo. We compare the effectiveness of the technique with static and path-sensitive motif analysis in the context of reducing recoveries, code coverage, and failure reproduction. In the first part, we show that our approach can reduce the number of recoveries, which is the number of dependencies on skipped functions that we encounter during the execution. In each program, we generate several configurations of skipped functions, and in every run, we check the number of recoveries per path. In the graph on the right, you can see the number of recoveries with each of the configurations, and on the left, you can see the relative reduction in number of recoveries compared to static pointer analysis. In the second part, we measure code coverage. We manually select the skip functions and measure the covered lines with each of the approaches. As you can see, our approach was able to get more coverage in all cases except of one case. In libOSIP, where we use DFS, the coverage with our approach was indeed lower, but when we exclude the lines of the skipped functions, since the coverage with our approach was actually higher. In the context of this application, it's good, since the goal is to explore the code outside of the skipped functions. In the last part, we evaluated the technique in the context of bug finding. We took the CVEs that were used in the work that introduced job symbolic execution, and for each CVE, we check the time that it takes to find the bug. So here you can see the performance of the two approaches with the DFS, and similar results were obtained with other search heuristics. Our second application is symbolic pointer resolution. In symbolic execution, symbolic pointers may point to multiple objects. To resolve them, we scan the memory, where for each scanned object, we construct an SMT query that checks if the pointer may point to this object. If our address space contains many objects, then we are expected to have many such queries, which can be very expensive. We can improve the situation if we use points to information. We can compute the points to set of our symbolic pointer, and then if we have an object which is not contained in this set, we can skip it and this way reduce the number of queries. So computing this pointer set with static point analysis is straightforward, but let's see how we can do it with our path-sensitive approach. If we have a symbolic pointer in this line, then abstracting the current symbolic state will not help us, since abstraction itself will require to resolve this symbolic pointer. So what we can do is to go up the stack frame and run the point analysis from the calling function. In the evaluation, we took several programs to generate symbolic pointers, and we compare three modes. We have baseline CLI and two modes that use point analysis. The first one uses static point analysis, and the second uses our path-sensitive approach. As you can see, our approach was able to get the best results in terms of analysis time and number of queries. Also note that in one of the cases in SQLite, the static mode was actually slower than the baseline, since the whole program analysis took almost 10 minutes. Our last application is with write integrity testing. This is a technique for detecting memory corruptions in runtime. Here, each pointer and object has a color, and if during execution we detect a mismatch between the color of the pointer and the color of the object, then we report a memory corruption. The color assignment or the policy is computed using static point analysis. First, we compute the pointer sets of each store operand. Then we merge intersecting sets until all the sets are disjoint, and each disjoint set corresponds to a unique color. We want to have a more precise color assignment, which means a more strict policy. Usually applications first run some initialization code, and only then run the core logic of the program. We can use our path-sensitive approach to first execute the initialization code, and only when it completes to compute the color assignment. In the evaluation, in each program we compute the number of colors and also record the number of color transitions. A transition happens when we have two subsequent allocations which have different color, which gives us a measurement for the possibility of detecting memory corruptions. As you can see, with our approach, we were able to compute more colors, and also the number of transitions was higher, except for the case of libdiff. A couple of words about future work. In this work, we integrated symbolic execution with pointer analysis, but this also can be done with other static analysis such as constant propagation, numerical analysis, and so on. We can also apply our technique with other types of point analysis, such as flow sensitive and context sensitive. Finally, we can come up with more client applications for symbolic execution, which rely on pointer analysis. To summarize, we designed a tighter integration between symbolic execution and pointer analysis. We evaluated our approach with several client applications, including job symbolic execution, symbolic pointer resolution, and write integrity testing. Our code is available on GitHub, and you can also visit our project page.